Good morning. Welcome to AP Statistics. Yeah. Wow. The studio audience today. Now, just as far as the makeup test goes, I will, if your grade drops below 70%, it's an eligibility issue, but it's up to the teacher. If your score on your Unit 7 test, it's in the grade book now is Unit 8, I'm gonna have to edit that. If your Unit 7 test causes an eligibility issue with you, I will not say that you're ineligible if you get your podcast notes into me by Tuesday, because Tuesday is the day that we make the decision. Potentially Wednesday morning when we make it. So if you signal to me that you're gonna take the makeup test, then I won't give you any eligibility issues that might have been caused by this test. So just keep that in mind. We're going to take another look at some new things that have appeared in terms of resources. I teach periods 4, 5, and 6, so I had yesterday off. Look at the fun I was able to have on the topic called general resources. I found a central limit theorem link that my Java program wasn't letting me look at it, but somehow I must have updated Java, and now I can actually, this is a central limit theorem link that has been oh so valuable for so long. I finally have access to it again. Now, the central limit theorem, which we started learning on Tuesday, has 3 statements. The central limit theorem was question number 1 in free response back on the first year that the AP test went big time. It was piloted in 1997. But question 1 was, what is the mean
value
of, no, it said, what is the mean of a sampling distribution of sample means? Part B, what is the standard deviation of a sampling distribution of sample means? And Part C was what is the shape of the sampling distribution of sample means? Now, we looked at the layers of concepts that are involved in the central limit theorem, but I don't want it to be a secret that we're looking at sample means. Suppose I take a sample of 10 of you, and instead of asking you, are you going to vote for Trump, I ask you, how tall are you? And I take the average height of the 10 people in the sample. And then I take 10 other people and look at their average height. So I've got X bar 1, X bar 2. And then I want to know what is the mean of the sample means. That's what word picture 8 is about. It's about the mean of the means. We take all these averages of samples of size 10. We say, what is the average of all the averages? And then we say, imagine an infinite number of samples of size 10. We ask ourselves, what is the mean of the sampling distribution of sample means? And so the answer to problem 1A was that the mean of the sampling distribution of sample means is equal to the mean of the population, the mean height of the population. Now, on your notes, I'd like you to just write down on the very last page, there's room at the bottom half of page 4 to write down all 4 statements in the central limit theorem. So let's just jot down all 4 of them. And here we go. On the bottom half of page 4, you can write the mean of the sampling distribution of sample means, the average of the averages. The mean of sampling distribution of sample means is equal to the mean of the population, the average height of the entire population. That was question 1A back in 1998. Question 1B, they said, what is the standard deviation of the sampling distribution of sample means? Answer, the standard deviation of the sampling distribution Once we put the ing on sampling, that means there's how many samples? There's an infinite number of samples. The sampling distribution has a model. The standard deviation of the sampling distribution of sample means is the standard deviation of the population is parallel construction is equal to the standard deviation of the population, and that's not the end of the sentence. What's the rest of the sentence? Yogurt day helps us calculate that. The end of the sentence is what? It's not overhead. What is the standard deviation of an average? We looked at that briefly at the end of the period yesterday. Again, suppose we have a population where the true mean is 75 inches and the true standard deviation is 5 inches. And we take a sample of 3 people. We'll define a random variable. Let x equal the height of a randomly selected person. So if we want to find the average of 3 people, what would we do to x1 plus x2 plus x3? We divide it by 3. So what's the standard deviation of x1 plus x2 plus x3 over 3? Or in other words, what is the standard deviation of x1 over 3 plus x2 over 3 plus x3 over 3. We saw it yesterday, but you should probably write it down in the margin, because this is the yogurt day connection with the central limit theorem. It's like we're yogurtizing x1 by a factor of 1/3. We're multiplying it not by 3. You know how sometimes you take a gloppy scoop of yogurt and yogurtize it by a factor of 5, so that once you put it into the yogurtizing machine, you suddenly have exactly 5 times as much yogurt?
Yes.
Have you ever imagined that?
Yeah.
I'd like you to imagine a gloppy scoop of yogurt that's yogurtized by a factor of 1/3. You put it into the yogurtizing machine, and suddenly you have exactly 1/3 as much yogurt. Who ate that yogurt? Where did it go? I want it back. No, it's gone, because now you have exactly 1/3 of it. So what is the standard deviation? It's the square root. The standard deviation of an average is the square root of, what's the standard deviation of x is 5. So now the standard deviation of the yogurtized amount is 5/3 squared. So the variance is 5/3 squared plus 5/3 squared plus 5/3 squared. Yeah, you probably won't get the connection to yogurt day until you actually write down an example. Think through an example on your own. How many of these 5/3 squared things do we have?
3.
3 of them. 3 of these 5/3 squareds. And when you, wait for it, do the math, you get 5 squared over 3 squared. A pair of 3's cancels. It gives us a square root of 3. No, that 3's gone. 3's gone, Mr. Royce. It's gone. It's no longer there. Yes. That canceled. That's 5 squared. 5 squared is still there over 3, or 5 over the square root of 3. That's the original standard deviation divided by the square root of the sample size. So, question 2 back in 1998 was, what's this? What standard deviation should we use for the normal model of the sampling distribution? Well, the standard deviation of the sampling distribution of sample means is equal to the standard deviation of the population divided by, basically over, divided by what? Who? Square root of the sample size. N is the sample size. Divided by the square root of the sample size. Okay. And then, part 3 was what's a shape? Shape, center, spread. Shape, center, and spread. Here's center, here's spread, so part C was shape. What's the shape of the sampling distribution of sample means? Here we go. The answer to problem 1C in 1998 was the shape of the sampling distribution of sample means is not normal for small values of n. Asterisk. There is an exception to that. Is not normal for small values of n, asterisk. The shape becomes more and more normal as sample size approaches infinity. The shape becomes, becomes more and more normal as n approaches infinity. As n, the sample size approaches infinity. Jack, you had your hand up.
So the sampling distribution of sample means, is the sample means, is that X bar?
Those are X bars. Imagine a sample of size little n equals 10. 10 people stand up. We measure them. We get those 10 heights. We add them all up and divide by 10. That gives us X bar. That's one sample mean. And then 10 other people. We get another sample mean. And then we get an entire sampling distribution of sample means. If we have an infinite number, then a normal model will be appropriate.
What's P?
That's a sampling distribution. We use p-hat when we're looking at the sampling distribution of sample proportions. So your question is asking about basically the difference between word picture 7, which is a central limit theorem applied to sampling distributions of sample proportions, p-hats, and word picture 8, which is about sampling distribution of sample means.
What's a proportion?
What is a proportion? Well, if I were to, it's basically a percentage. So if I were to take 10 people, say, are you going to vote for Trump, and 6 of them said yes, then that would be like the value of the random variable x. X is the number of people who are going to say yes and vote for Trump. You can turn x, which has an expected value, the expected number of people who are going to vote for Trump is NP. You can turn that into a proportion by, get the expected value of p hat, by taking the people and dividing by n,
It's just P.
p.
Yeah.
So the expected value, basically take however many people said yes, I'm going to vote for Trump, and divide by the sample size. That's how you get your p hat. So p hat is number of successes divided by the sample size. 6 over 10 is 0.6. Yes?
Can you move so I can see the rest of the board?
Yeah.
It doesn't matter, just over.
Oh, you want me to move over?
Over. Thanks.
Okay.
Wait, so
I thought you just wanted me to move. Yes, go
in
ahead.
that table, that P, it's not P hat. That's not
Right,
probability though either.
No, p hat. So what Olivia's question does is it raises the issue that the letter P is used in at least 5 different ways in AP Stats. P is used for probability. It's used for the true proportion P.
That's what it is there.
This is a sample proportion P hat. It's used for the hypothesized proportion P sub 0. So yeah, the letter P shows up. Oh, and then it also shows up for the p-value, which is the probability of a. It's a probability of a conditional statement. You know, the probability of the eyeball statement given the brain statement is what's called a p-value. So there's 5 different uses. And so part of what will be coming together in this semester is you'll get really comfortable. with all 5 uses of the letter P in this course. So it's understandable that you'd be, wait, what? P represents what? 5 different things.
But for this one, in word picture 7, P is the true proportion.
We have 2
P hat.
P's in word picture 7. We have the true proportion P without the hat. That's the true proportion of people who are going to vote for Trump.
And like
And then we have the P hat. P is the mean of the infinite number of samples. Each individual one is called a P hat. That's right. The God's eye perspective is the P value. I'm sorry, the true proportion P. I can't say P value. That's a different use of the letter P. Now, let's talk about the asterisk. The shape of the sampling distribution of sample means is not normal for small values of n. And that's where this little applet comes in handy. Suppose you have a population of voters, or let's go back to heights. Let's do sample means. Let's say you have a population of people you have some tall people, some short people, but a lot of people in the middle. It's bell curve distributed. It's normally distributed. And suppose you take samples of size 1. What would be the sampling distribution? What would the sampling distribution look like? Well, what they do here is they take, if I press draw, what they do is they take samples of size 1 from a population. They take 32,691. That's actually the population size. That's capital N. So there's 32,691 people in this computer-generated simulation of a population. And the tallest person, I guess, is 100 inches. The shortest person is 0 inches. A pretty short dude. But the average, the mean of these samples.
Wait, so are these all X bars? Is it 32,000 whatever X bars, or is it just one survey with 32,000 people?
Yeah, so that's a reasonable question, and I think it's here. If we do population size small and draw, yeah. So I think that's just the number of samples. That's a population of samples. We don't know what the population size is. They took 10,637 samples, X bars. So this gives you an idea of what the sampling distribution looks like, because it just takes small. I mean, high. How many X bars are we going to take now? Well, it takes longer for the computer to do this because it's randomly calculating samples of size 1 in a normally distributed population. And it's probably going to be a pretty big number here. How many X bars? 106,000 X bars. But what if we have a population that looks like this, where no one is of average height? You've got a lot of really, really short people, a lot of tall people, but no one is in the middle. We take samples of size 1. And let's stop that. Let's go medium, because high takes, stop. Medium is better because it doesn't take as long. So if we do samples of size 1, I guess it makes sense that we'd have a sampling distribution of sample means that matches the population. And that's where the word not comes in. What's the shape of the sampling distribution of sample means? The shape is not normal. The shape of the sampling distribution of sample means is not normal for small values of n. This is sample size 1. And I'd like all of you to do an air sketch of the shape of the sampling distribution of sample means. Just go like this. Do an air sketch. Okay. I'd like all of you to do the air sketch. What do you predict the air sketch will look like when I go to sample size 2? What if I take samples of size 2? Go ahead and do an air sketch. I'm seeing people go like, okay, here's what I think it's going to be. I think it's going to be like this.
What? Me too.
I think it's going to be really high in the middle.
That's what I was saying.
I think it's going to be really high in the middle. Here's why. Watch this. I'm taking 2 people, randomly selecting 2 people from a population that's distributed like this. Like if I get 2 short people, then the average height will be short. What if I get a tall person, or a short person and a tall person? What's their average going to be? Somewhere in the middle. What if I get 2 tall people? Their average height will be pretty high. I think it's gonna go like this. I think it'll
I
go
think it'll be this.
1, 2. Let's find out.
It's like a bracket.
Samples of size 2. Interestingly, row 2 of Pascal's triangle is 1, 2, 1. Let's take samples of size 3. We're going to take 3 people randomly selected from a population in which no one is of average height.
1, 3, 3, 1.
Do it to me.
And it's a sort of thing where, I guess, if I were to imagine what's going to happen so I can get ready to do my air sketch, I'm going to ask you to do your air sketch pretty soon. But remember that the first person in this population is either tall or short. In fact, let's even go like this. Let's do, the first person's either short or tall. In this population, it's pretty much, we have a lot of short people. I mean, yeah, there are some people close in the middle. The second person will be on the short end or the tall end, short, tall. The third person we pick will be either short or tall. And we're gonna have 8 leaves. And sometimes we'll get 3 short people and we'll average their heights. Well, 3 short people, SSS. Well, sometimes we'll have short, short, tall, and I think it's gonna be, since I know that row 3 of Pascal's triangle, 1, 3, 3, 1. I think there's gonna be one of those 8 samples. In fact, if I were to I'd take one of those, we'll have 3 short people. 3 out of 8 times, if I were to do this 8 times, 3/8 of the time, I'll have 2 shorts and a tall. 3 out of 8 times, I'll have 2 talls and a short. Only 1 out of 8 times. Would you please do an air sketch of what you think the sampling distribution of sample means will be shaped like? If you're doing like 1, 3, 3, 1, let's find out. Let's see what this says. Draw.
Yeah.
Exactly. I was right.
Tree diagram, 1, 3, 3, 1. There's 8 leaves collected into 4 categories. 1 out of 8 times you'll get all 3 short people. 3 out of 8 times you'll get 2 shorts and a tall, 1 short and 2 talls, 3 talls. Now, look at the central limit theorem. It says that the shape of the sampling distribution of sample means is not normal for small values of n. It could be like this, not normal. It could be 1, 2, 1, not normal. But what is the second half of that statement, Olivia? What's the second half of statement 3 that you wrote down?
It becomes more and more normal as it approaches infinity.
As what approaches infinity?
As n approaches infinity.
And what does n represent?
The sample size.
The sample size. Let's increase the sample size to like row 5 of Pascal's triangles. 1, 5, 10, 10, 5, 1.
Oh, decrease.
Yeah.
So increase the sample size, decrease the sample size. What if we're taking 5 people and averaging their heights? 1, 5, 10. What does the shape of the sampling distribution appear to be approaching?
More normal.
It's more and more normal. It's a sample. Suppose I take samples of size 10 people from this population, even though the shape of the population is nowhere near normal. This is what the mathematician named Laplace proved in the year 1711. Or was it 1811? It was either 17 or 1811. And the math community was up in arms. It can't be. What do you mean we can always use a normal model as long as the sample size approaches? You know what? You're always going to be able to use the normal model for the model of the sampling distribution of sample means. What if the population is non-normal? Laplace said, no. I proved it. The shape of the sampling distribution of sample means becomes more and more normal as n approaches infinity. The sampling distribution of sample means has a mean that is equal to the true mean of the population. The standard deviation of the sampling distribution of sample means is the same as the standard deviation of the population divided by the square root of 10 in this case. And the shape of the sampling distribution of sample means becomes more and more normal as the sample size approaches infinity. What if we have a sample size of 20? That's pretty close to infinity. It just becomes more and more normal. And what's happening to the standard deviation? What is happening to the spread of the sampling distribution of sample means? I mean, compared to what it was when the sample size was 5, when the sample size was 5, look at the spread, it's becoming more and more normal. What's happening to the spread as the sample size increases? Yeah, if the standard deviation of the sampling distribution of sample means, sigma sub x bar is the true sigma over the square root of n. As n increases, notice n is located in the denominator. As n increases, what's happening to the value of the fraction overall? It's decreasing, and you can see that in the applet. You have access to this applet so you can review what's going on. In fact, you can take any distribution you want. Now, if the population itself is already normal, then even when the sample size is 1, then the sampling distribution of sample means will still be normal, even if very small sample size. That's the asterisk. If the underlying population is normal, then this statement does not apply. Friends, that's the asterisk, and then I'll take Olivia's comment or question. So, the asterisk is on the shape, and we have to define what the asterisk is. Asterisk, unless, and yeah, please wait till I call on you, and then you can talk. Unless the underlying population is normal. Yes.
Wait, so for, because that sampling size was so like polarized, like there's like only tall people and only short people, what if it was just like skewed left? It still works.
Okay, and they have that kind of stuff in the applet also.
Yeah.
They have 8 different populations.
Like
So here's a skewed left population. In fact, here's one that's skewed right. So let's take population 7, it's severely skewed right, correct? Do we agree? So let's take samples of size 1. The sampling distribution of sample means is skewed right. But as the sample size increases, the sampling distribution of sample means has a shape that becomes more and more normal. If we randomly select 16 people, then we just get a normal distribution. And it's centered around the mean. Since the original population is skewed left, the mean is not at 50. It is left of 50. It's at 38.7. That makes sense. And so the sampling distribution of sample means has a mean that points to the truth. It points to the truth. So that's a great motivation for coming up with sampling distributions of sample means, because the mean of that sampling distribution of sample means, it doesn't even have to be, I mean, we're not going to come up with a sampling distribution by observation, because we could never take an infinite number of samples. But we could get a large number of samples, and the mean of that large number of samples, or even if you get just one sample, which is what statisticians do, they just get one sample, and they say, well, the true mean can't be too far away from our sample mean. And so, but they want the truth, they want the sample mean, want at least approximate. So that's why we need a formula for the standard deviation. So this is what we need to be able to say by the test, which is 1 week from tomorrow. You need to be able to say, this is your script. You need to be able to say all 3 of these. So let's practice these. Try to do it from memory. If you need to look at your script at this point, that's fine. But I want you to say out loud and in unison, the mean of the sampling distribution of sample means is equal to the mean of the population. Ready? Go.
The mean of the sampling distribution of sample means
Is equal to
the mean of the population.
statement 2 in the central limit theorem. Center shape, wait, hold on. Statement 2 is, class, ready, go. The standard deviation
Of the sampling distribution of sample means
is equal to
the standard deviation of the population
divided by
square root of the sample.
divide by the square root of the sample size. A lot of people forget to divide by the square root of the sample size. And third, this one, because of the asterisk, here's how we're going to handle the asterisk. When I say go, I want you to say the shape of the sampling distribution of sample means is not normal for small values of n asterisk, and then say unless the underlying population is normal. and then go on, the shape of the sampling distribution of sample means. So go ahead and use parallel construction. The shape of the sampling distribution of sample means becomes more normal as sample size approaches infinity. We're not for small value. Okay, so we can say as n approaches infinity. Here we're saying n twice. As n approaches infinity. Let's try it. Ready? Go. The shape of the sampling distribution of sample means is not normal for small values of n asterisk unless the population is normal. The shape of the sampling distribution of sample means becomes more normal as n approaches. Sample size 2. Sample size 3, 1, 3, 3, 1. So Pascal's triangle becomes more and more normal. So yeah, we see it. All this work we've been doing has been leading up to the central limit theorem. So that's it. That is the central limit theorem, or at least the version that applies to sampling distribution of sample means. Now, back on your big handout, we were on page 2 where there was this phrase, central limit theorem. We said, I have to teach you what the central limit theorem is. So we went and did that. Let's go back to page 2, and I'm going to pause the camera while I open that document. Okay, friends, we're in the part 1 of 2, coin tosses, and we encountered this phrase. That's when we took a little detour. So Will and company, let's refocus. Remember, we're taking, in a stats class, the professor has each person toss a coin 16 times. So the probability is 1/2. This is like an underlying normal distribution. And so the central limit theorem is not really coming into play here. So where do you expect the histogram to be centered? Well, we expect, and this is, think word picture 7 here. We're not looking at sample means here. We're taking a look at sample proportions. The histogram is expected to have a center at 0.5. On average, we expect that half of the coin tosses will give us heads. How much variability would you expect? This is square root of PQ over N, so you're expected to be able to perform the square root of PQ over N calculation. And the expected number of heads, this is no surprise, this is word picture 7. We have mu sub p hat equals p, the true proportion, and the standard deviation of the sampling distribution of sample proportions is the square root of PQ over N. Those are the formulas that were used in parts B and C. And then it says, explain why normal model should not be used here. Now, on the test, by the way, when they ask you that question about should a normal model be used, if it's already known to be a binomial situation, then all you have to do is look at NP to see if it's greater than 10, and NQ to see if it's greater than 10. Now, but if you don't already know that it's a binomial situation, then you have to see if the sample size is too big or too small. I mean, it can't be too big. So, speaking back to that problem on the test, you do have to look at 10 little n is less than big, and that's the third question that you have to look at. If you didn't ask that, I didn't take off for that. So, but I just want to let you know that when you're looking at the question of should a normal model be used, yeah, we do have to look at NP and NQ. And here, right away, NP is not greater than 10. No. That's called the success condition. NQ is called the failure condition. So the success condition is not satisfying. Therefore, the success-failure condition is not met. The normal model is not appropriate in this case. That's page 2. Please flip over to page 3 of your notes. More coins. And I'm all ears. Olivia, if there's something I need to hear, I'm all ears. I'm listening.
Come to worship night tonight.
Tonight's worship night is one thing I'm hearing.
Yeah.
And basketball.
Anything else? All right. There's a basketball game. When's a basketball game?
Worship night's at 7. Basketball game's at 7:30.
You
Good.
can make it to
But nobody even wants to watch the first half of the basketball game. So you
What are
still
you
worse
calling
than
it?
I agree.
Nobody.
The
Oh,
first half is
actually,
I want to watch the first
Yeah.
half of it.
You gotta,
What if I wanted to vote?
yeah.
Well, thank you for sharing,
Yeah,
appreciate that, I didn't know those things. Now I'd like you to focus in on problem set.
No one's supposed to participate.
Yeah, cause they're not on our side.
We're gonna look at more coins in problem set. So now suppose the class in exercise 5 repeats the coin tossing experiment, but this time every student tosses the coin 25 times each. So notice that affects the standard deviation. I mean, if you're tossing a coin if you're tossing it just 2 times, then you could get 100% heads. Wouldn't be too surprising. But if you're gonna toss a coin 25 times and you get 100% heads, a P head that's way above 50%, it's like averages do not get spread out. And as the sample size goes up, the standard deviation goes down, and your sampling your sample distribution, which we called in layer 3 the distribution of samples, in this case the distribution of sample proportions, is going to have a smaller standard deviation. Compare that to the standard deviation on the previous page. When n was 16, we had a standard deviation of 0.125. But as the sample size goes up, the standard deviation goes down. Why? Because n, again, is in the denominator. When the sample size is in the denominator, then bigger sample sizes lead to smaller standard deviations. By the way, reviewing from semester 1, the 68, 95, 99.7 rule, that was chapter 6, unit 2. We go plus or minus 1 standard deviation to get 68% of the distribution, plus or minus 2, plus or minus 3. That's just review from a long time ago. Confirm that you can use a normal model here. Well, we gotta look at the success failure condition. There's no need to check the 10% condition because we have an infinite number of possible coin tosses. We have to look at NP and NQ. NP and NQ are both 12.5. Oh, finally, greater than 10. So since the success failure condition is satisfied, we can use a normal model with a mean of 0.5 and a standard deviation of 0.1. Then we can answer questions. So what if they increase it to 64? If n is 64, the standard deviation keeps shrinking. Now it's down to 0.06. And yes, clearly, that's no surprise here. Last page, let's go to page 4. I knew we'd be doing a lot of talking about air sketching. That's where the emphasis was today, so I didn't want to have you waste a lot of time taking notes. But what's going on? As the number of tosses increases, the sampling distribution model will still be normal, centered at 0.5, but the standard deviation, as we've seen, keeps shrinking. The standard deviation goes down and down. The sampling distribution model will be less spread out. We saw that in the applet. We see this in the algebra. Now, one of the students in the introductory stats class in exercise 7 claims to have tossed her coin 200 times and found, whoa. Your sample size was that big, you're tossing 200, and you got only 42% heads? What do you think of the student's claim? So what is the null hypothesis when a human being makes a claim? They're telling the truth. And an exception to that would be if they're making a claim about the future and they happen to not be a prophet with an established track record of predicting the future. So if someone's predicting the future, you assume that what they say is false. Okay? I mean, like, for example, weather forecasters, you tend to think, well, they're a professional. They're not just anyone. They're predicting the future, but they're trained. So if it's a weather forecaster, we'll assume null hypothesis that what they're saying is true. But if they're just a random person who's predicting the future, not about the weather, but about, it's like, wait, how can you know that? Like, there's going to be an earthquake in San Francisco tomorrow morning at 9:23 a.m. It's like, okay, I'm going to assume that you're not telling the truth. So you have to think carefully about what the null hypothesis is. But if someone says, I mean, okay, in this case, we're going to assume that you're telling the truth. So the null hypothesis, N sub 0, I'm sorry, H sub 0. H is the first letter of the word hypothesis. H sub 0 is she's telling the truth. Some of you were wrestling with this issue on the test when it came to someone saying, oh, like on the practice test, Gilbert said, I was just guessing. On all 80 questions on the test, I was just guessing. And I got 25 correct, just by guessing. So you assume he's telling the truth, unless you get a really low p-value. If the probability that we observe Gilbert getting 25 or more questions correct, given that he's telling the truth, is too low, then we're going to reject the null hypothesis and say that Gilbert was not guessing. He must have had he must have been thinking, or he had access to some of the answers. Alternate hypothesis, she's lying. Okay, so for 20 flips, but I'm sorry, I should say for 200 flips. Add a 0 there. For 200 flips, the sampling distribution is normal with a mean of 0.5. So the mean of the sampling distribution of sample proportions is the same as the mean of the population, which is 0.5. Then the sampling through the standard deviation for sample proportions has this formula for the standard deviation. The square root of PQ over N comes out to really tiny, 0.034. So notice that 42%, that's about 2.26 standard deviations below the mean. If we were to take the time to do all this, we'd be like, mean is 0.5. She said 42%. So we could get a z-score for that using the standard deviation. We could say, and we didn't fill this in, I hope you have your word picture, but we did not fill in the new z-score formula. And it's right here. This is P, you have square root of PQ over N. Here's mine, you've got your calculator, we'll just watch the cable there. And just check the calendar online, except when
你看它这里只给我扣了一个，这是3，然后其他是4和4，但是它这里写的是29还有32。你那后面有扣分吗？
没有，
你是444吗？
我
那他为什么是29和32？
一定让他把我做的给我按上，因为
哎呦我
一到第3分，
不可能啊！他上面给我写的是，他写的是
You don't have to
34、32的话对，但是他有考试，我不然
Good morning, we come down to school. Because everyone who gets 11 12 because 11 12 is about 29 over 32. What did your email say?
I sent with you about like a practice test that like days before, like and you said you will like remember to enter the grades for me, but it's still a 0 now.
On the practice quiz?
Yeah, practice quiz.
Practice quiz.
Yeah.
Let me fix that right now.
It's the first one.
All right, you know what? My computer is glitching right now, but I'm gonna stay here, I'm gonna fix it, so I have to trust me on that, and we'll see. Let's fix, okay?
Okay, thank
All right, thank you. All right, Lauren, what's on your mind?
Yeah, so today is the last day that I have anything related to cheerleading, but I can come after school really quick for help on like the homework that's assigned tomorrow. And for the test, I could just review that myself, and I could take it sometime tomorrow. I do have a study hall during 6th period.
Well, I teach during 6th,
Okay.
but okay, it sounds like we're planning. I'll be here shortly after school Wednesday.
All right. Thanks.
All right, thank you, Lauren.
Only drops.